All right, this video is going to be about how to use substitution on indefinite integrals. We call this method substitution because we are literally going to take every single x and replace it with some part or some other variable u, where u and x have to have some type of relationship. It's also called change of variables because we're literally changing the variables of the expression so that it's easier to work with as far as applying the integration rules. Here is the actual substitution with indefinite integrals definition. We're going to go ahead and jump in and solve this first one here. So the best place to find what we want to call u is we want to call u the most inside function. We are essentially undoing chain rules. So we want to make sure that we are able to find the inside composite function piece. So I'm going to let u be equal to 3x squared plus 4. And so when I rewrite this integral, I have 6x times u to the 4th dx. Well, I need everything to be in terms of u. I don't need these extra pieces here. I want to now integrate this with only u's in there. So I'm going to rewrite this as u to the 4th, and then I'm going to write this together as 6x dx. And I need to figure out, in terms of u, what could I write instead of 6x dx? So I'm going to take the derivative of this, because that's how I find du. And I'm going to take the derivative with respect to x. And when I do that, I find out I get 6x plus 0. And I can move this dx over here. So it just so happens 6x dx is du when we define our u as 3x squared plus 4. So I can write this as the integral of u to the 4th. And then in place of 6x dx, I'm going to put du. This is now an integral that I can find the antiderivative of using our power rule. So I'm going to have u to the 5th over 5, or times 1/5. And it is an indefinite integral, so I'm going to say plus c. And then I'm going to plug u back in. So 1/5 times 3x squared plus 4 to the 5th plus c. And one thing you can always do is take the derivative of your answer and see if you get back to your integrand. So 5, bring it in front, those cancel. I get 3x squared plus 4 to the 4th, and then times the derivative of the inside. Yes, that is what gets me back to my integrand, so that must be my antiderivative. All right, let's look at another example here. So use substitution to find this integral. Again, the thing that is going to be u is going to be our inside piece. So I'm going to let u be equal to z squared minus 5 because that's inside. And so if I do that, then I have the integral of z times the square root of u times dz. Well, I don't like these pieces here, right? I want those to be in terms of u. Well, let's figure out what du would be. Du would be equal to 2z. And then we do write du dz, but then we end up moving it over to this side. All right, well, I don't like this z dz, so I realize here that z dz, that's really difficult to say, would be the same thing as 1/2 du if I just move that 2 over. So what does that mean? That means that z dz, I can have 1/2 du, and then I can place the square root of u on the inside. This is u to the 1/2, so I have u to the 3/2. I have this 1/2 in the front. I'm going to multiply that by 2/3. That's the same thing as dividing by 3/2 plus c. These cancel, and I get 1/3. This inside u piece is z squared minus 5 to the 3/2 plus c. And you can go ahead and again take the derivative of this antiderivative and see if you get back to the integrand. And in this case, we definitely do. All right, we have one more example here. I have cosine cubed in the denominator and sine in the top. Now, whenever you have a fraction, it is very tempting to make the entire denominator the u piece. However, one thing that I can kind of think of ahead of time, since I've been doing this for a bit, is if I let this be u, I don't know that I have a full chain piece of du that I need to get rid of here. So I don't think that's the correct u. Instead, I'm going to let it just be cosine. And I know it should be cosine because I see I have a sine t here, and I should start seeing that, start to see that composite piece with the derivative, that chain rule piece with that derivative, and that's going to help you find what your u is. All right, we can rewrite this originally as sine of t times 1 over cosine cubed dt. So if this is my substitution, then I have 1 over u cubed. Now, I don't like these things being here. I need everything in terms of the same exact variable. So let's go ahead and find du. Du would be negative sine t. I'm going to go ahead and write it as dt. I only have a positive sine t dt, so I'm going to switch that over. And so in place of sine t dt, I'm going to plug in negative u. So I have 1 over u cubed, and I'm going to go ahead and just take that negative outside. Rewrite this as u to the negative 3. I get u to the negative 2 divided by negative 2 plus c. Those become positive. 1/2. What did we end up calling u here? Cosine, right? Cosine t squared plus c. And a nicer way to write this might be 1/2 and then cosine squared t plus c. Again, you can take the derivative of that and make sure, oh, to the negative 2. I cannot write that. All right, let's do this. Let's do this math better. I have u to the negative 2, so I have 1 over cosine squared t. Now that's 1/2 secant squared t plus c, and that right there is what my antiderivative is going to be.